Assalamu alaikum warahmatullahi wabarakatuh. My name is Siti Aisha Muhammad Razaidin. I am from Group 11 and I will be explaining regarding the detailed design of a major equipment for the carbon dioxide stripping column. Let's get started. Now for the outline of today's presentation, I will first begin with the introduction, followed by the design methodology, and finally I will display the drawing and specification sheet. For the introduction, the process plan that we designed involves removing carbon dioxide and sulfur dioxide from gas, as well as producing two value-added products. Now the unit that I have selected is for solvent regeneration of carbon dioxide. And this CO2 stripping column will be designed in such a way a reactive distillation column is being designed. Now this diagram displayed is the schematic diagram of the reactive distillation column of this process. I will now proceed with the design methodology where it is split into two parts, the process design and the mechanical design. For the process design, it will then be further split into three main parts, which is the column operating conditions, the column sizing, and finally the column internal diameter. First up is the column operating conditions. Here we can see the properties of the feed stream, distillate, and bottom. The number of trays is 12 columns, and the feed tray is located at the 8th tray from the top. The components of the streams are also displayed in this table here. Next is the column sizing, which involves the column height and the column internal diameter. So the standard plate spacing we took is 0.45 meters with a 15% space allowance, and the number of trays determined just now was 12. So plugging it into this equation, we can determine the height of the column, which is 6.21 meters. Now for the column internal diameter, the first thing we want to determine is the liquid vapor factor because with this, we will look at this chart to obtain the K value. Assuming an 85% flooding at max flow rate, the flooding velocity is then calculated to be 1.411 meters per second. The net area and cross-sectional area can then be determined with a 19% downcomer area. With this, the column diameter is calculated to be 0.5575 meters. For the internal sizing, we will first have to determine the wear length by calculating the ratio of the downcomer area to the cross-sectional area. At 12% here, we retrieved a wear length to internal column diameter ratio of 0.75, which also gives us a wear length of 0.418 meters. Next up is the plate design. As we calculated just now, we can see from this table here the column diameter, the internal column diameter, the cross-sectional area, downcomer area, net area, and finally the total pressure, the total drop. So we do this by calculating the minimum and maximum height of the liquid crest using this following equation where LW is the wear length calculated previously. We then calculate the dry plate drop and the residual head here. The sum of all of it is the head total drop. Now, weeping point happens to be a phenomenon that occurs inside a distillation column whereby it is caused by very low vapor flow. The weep point velocity has to be at a minimum value so that our actual vapor velocity has to be higher so that weeping doesn't occur. So we do this by calculating the minimum and the maximum crest height and retrieving the constant K from this graph here. We then plug it into this equation to determine the minimum vapor velocity. So since our actual flow rate is higher at 37.18 meters per second, then our operation is stable. So another thing to calculate is the downcomer liquid backup, and this is very important to avoid flooding. This is very simple. All we need to do is just ensure that the downcomer backup HB that we calculated meets this criteria. If it does, then flooding can be avoided. We will now move on to the mechanical design of our vessel. Regarding the selection of this material, I have selected the stainless steel since this column will deal with ammonium hydroxide solution and avoiding corrosion is necessary. This design pressure will be taken at 10% above operating condition, leading us to 4592.5 kilopascal. The design temperature, on the other hand, is taken at maximum value, and the design stress of stainless steel at this specific temperature is known to be 145 Newton per millimeter square. So the main specification I will focus on is the shell thickness, closure height, head volume, total height of the column, and the nozzle diameter, which will be displayed in the drawing sheet. So for our vessel, a torus spherical head or a dish end head is selected as the end closure for this vessel because our vessel operates below 15 bar. Now using this calculation here, we get a shell thickness of 2.901 millimeters, including the 2 millimeters corrosion allowance. So the height is taken to be 0.5 meters and the volume using this calculation is leading to 0.02688 millimeters square. Therefore, adding this to the closure height to our column, we get a total vessel column of 7.21 meters. Now the diameter of the nozzles can be calculated using this value here, and it can then be displayed in the drawing and specification sheet. So as you can see in this drawing sheet, we can see the specifications of our column here, where the diameter of the feed nozzle, vapor nozzle, and liquid nozzle is being displayed. The height of the column is taken at 7.21 meters, which is inclusive of the closure of 0.5 and 0.5 meter. This is the sieve tray drawing where we can see the wear length and the column diameter. This one is the spacing between the two plates, known to be 0.45 meters, and the thickness of the plate at 50 millimeters. And this one is the whole area that is on the plate, which is 0.005 meters. This is the specification sheet, all which includes the unit that we have calculated in our report, as well as that we have demonstrated in the presentation earlier. So with that, I end my presentation. Thank you.